induction, which is a proof. It is a proof, which means there are steps you must follow in order to get full credit for a proof. So take a look at this slide. This is a new kind of proof, and it has many applications or many uses, but we're going to use it today, and what you're going to be responsible for is to prove that a finite sum can be represented with a single formula in terms of n. So that's what this says here. This is a finite sum, so I'm stopping. This is my sum. I'm stopping at some arbitrary number k. These are the terms of my sequence that I'm summing up, but that finite sum is equal to a pattern, a rule, single rule, in terms of just how many terms I used. So what you must do is write out. You must write these steps out. You're going to write that the statement is true for when you use the first term. Then you're going to assume the statement is true for n equals some arbitrary k. Stop at 2, stop at 5, stop at 10. This is your work. This takes a lot of algebra, factoring, fraction work, all that kind of stuff. And you're going to prove it is true for the next statement, or the next term. K plus 1 is the next term, and you're going to use the previous statement. That's what makes this an induction proof. Kind of think of it almost like a recursive proof. Then this is also quick. Just you got to state your conclusion that the original statement is true by mathematical induction. So notice this little picture of the dominoes falling over. This is kind of what I think of with a math induction proof. It's kind of like somebody gives you a statement that is true. You say, hey, it checks out once. And then if it checks out once, then I'm going to say it's going to be true for when n is equal to k. And if I can prove then that it is also true for the next one, that's my domino pushing over. If this is my k domino and I'm able to prove k plus 1 could be any of these dominoes, and it just knocks them all over, right? Because if I say k was 2 and I prove it for k is 3, well then I'll choose k is 3, and then the proof still works for k is 4, and if I choose k is 4, the proof then works for k is 5, and so on and so forth. So this is a domino proof. All right, so all I'm going to do here is just do a bunch of these with you. So use induction to prove this finite sum, which is generated by these terms of the sequence, add them all up, can be represented by just whichever term you had squared. That's pretty crazy, right? Now I have to say that usually your problems aren't written like this. They're usually written like this, where they actually give you the first couple of terms so you can kind of see the pattern. And then they ask you to prove it for all n. And again, we're talking about where our terms are elements of the natural numbers, right? Here's an even fancier way to write this. I think it's funny. For all is an upside down A. Now, most of your directions will just say, on a test or something, it'll say like, or on your homework, the handout will say, use induction to prove that the following statements are true for all positive integers, right? This is just me showing off with some language. All right, so you must write, show the statement is true for the first case. So notice when n is equal to 1, and I'm going to assume 1 unless I'm told otherwise, that that's where I'm starting. So I put 1 in and I verify it's true. Yep. Next, assume the statement is true for n equals k, which is just a copy and paste from the given statement and replace n with k. Then you need to prove the statement is true for the next term. Now I want to go back here and I want to look and see what's going on here. We proved that it is, right, that if 1, the first term, is certainly equal to 1 squared, but nobody asked us, but look at the sum of the first 2 terms. Isn't that 4? And what is 2 squared? Oh my Lanta. What is the sum of the first 3 terms? 3 terms. What is 3 squared? Oh my goodness. This is looking pretty good. So I just have to prove it for the second term, which then proves the third, fourth, fifth, and sixth, and all that. So what I have to do is write the original statement plus the next one. Do you see where that is? Here is the next term. So this is like me stopping here after the second term and saying 1 plus 3 is equal to 4, which is 2 squared. And then saying, well, the n plus 1, so 2 plus 1 sum is 5, which is 9. 9 is the n plus 1 term. So that is the third term squared, right? And we're just using k's in the proof. Okay? Now, the next step is also going to be the same every time you're doing these problems in your proof statement. You want to clean this up. I would really like not to have that in my proof. Do you see a different way to write all of this? Hint. All of that is equal to what? Oh, snap. Now, when you're doing these proofs, most of the time you leave the right-hand side alone or do some minor changes. Don't go crazy on the right-hand side trying to simplify that. I am not going to expand that out. Okay? I'm going to look at the left-hand side and work with it first. Now I said I might do some minor cleanup to the right-hand side, but that's about it. This is 2k plus 2. 2k plus 2 minus 1 is 2k plus 1. And then my factoring brain, oh my Lanta, what does that equal? The right-hand side. Don't forget your last step is to write a conclusion. Technically, you should write out the statement again, but I'm not going to do that. Here's what you're allowed to do, what I am okay with you doing. This is proven by math induction. Okay? That one was pretty nice. But it's a pretty cool statement, right? The sum of all the odd numbers is equal to wherever you decide to stop is equal to wherever you decided to stop that term squared. Pretty powerful. All right, here's another one. So remember, the first step, you must write this. Okay, you have to write, and if you're doing a math induction proof, you must write this out. And you can abbreviate. Show true for n is equal to 1. Verify that this is true. And it is, right? 3 minus 2 is 1. This side ends up, the numerator is a 2, but 2 divided by 2 is 1. Next step. Assume true for n equals k. And yes, you have to write that out, which is just a copy-paste with k's in place of n's. Prove true for the next term. This is going to be your domino push. right? So notice that I took everything here, copied it over here, and then I wrote the next term, and into here I plugged in the next term into the formula, right? Now do your replacement step. So notice I used from my assume step. That's what I did. And now I will go ahead and clean this up a little bit. But just a little. This is 3k plus 3 minus 1. So I'm going to do the same here. Three k plus 3 minus 2 is 3k plus 1, right? But notice this piece is over 2. And this piece ain't. Can you fix that? And further, notice that where I'm trying to go on the right-hand side is over 2. Everything's over 2. So I think I'll probably make this over 2. So now I'm starting to get where I want to go. And I'm going to go ahead and put all of this on top of one fraction bar. Oh, Lanta. Look at what that is, though. So do you see why it's important to be able to factor and factor quickly? Now, I'm going to guess, since this is what I really want, right? I want a k plus 1 and a 3k plus 2. So I have a k plus 1 and a 3k plus 2. I'm going to guess that that's what it is and then verify. Is it true that these two factors equal my numerator? And if it doesn't, I'm going to go back and see where did I make, did I make a mistake somewhere? Because these proofs are going to work out. So is it true? 3k squared. 3k squared, yes. 3k, 2k is 5k, 2k plus 1 is 2. Yep. I don't really care about the order. Multiplication is commutative. Sweet. All right, here's our next one. Take a minute to copy that down. Okay, take a moment to verify that this is indeed true. Copy and paste. Add your next term. Next, next, next. Clean it up. Clean the right-hand side up a little bit. Do your replacement on the left side. So here's my replacement. Wasn't all that much nicer, was it? And then I'm going to clean this up. 2k plus 2 plus 1 is 2k plus 3. And then notice over here that I can kind of already see this has a denominator of 6. This doesn't. And my final result has a denominator of 6 with 3 factors, right? So the first thing I'm going to do is make that with a 6. So this now is everybody on top of 6. Now I'm going to leave the right-hand side alone and work just with the left-hand side. Factoring, factoring. How many k plus 1s do I have over there? How many k plus 1s do I have over there? And notice one of the factors that I want is a k plus 1 on the right-hand side. So I think I'm going to pull out the 1/6 and the k plus 1. Boom, boom. And what do I have left when I do that? I've got a k, I've got a 2k plus 1, I have a plus, and I have a 6 with a k plus 1. What do I have now? Factor. I think I will guess the factors that I want and see if that works. Is it true that 2k squared, 2k times k is 2k squared, then I have 4k and 3k, which is 7k, and 3 times 2, which is 6. Yes, that equals the right-hand side. What? Let's keep going, kids. Bull. What is this? Okay, look at your equal sign. And maybe you want to try this without me. Show true for n equals 1. So go to the formula. This time I didn't bother typing all these out. 1 times 1 plus 1, that's equal to 1 over 1 plus 1. True. Prove. So don't forget what you're going to add here now is the next term. Right? So clean that up, but not too much. Right? Don't do this too much. So I will say that the right side is k plus 1 over k plus 2. The left side, you already know what what you're going to replace there. That's going to be k over k plus 1, right? From your assume step, plus 1 over k plus 1 times k plus 2. Hey, I already see that what I'm trying to show, I've already got one factor in the denominator. Now look at these, so I'm going to work with the left-hand side. What's true? I have two fractions, but I can't put them, and I only have one fraction in my final where I'm trying to go, so I think I need to put those fractions together, which means this fraction needs to be multiplied by a k plus 2, right? So I have k squared plus 2k plus 1 all on top of k plus 2 times k plus 1. But look at that numerator. It's a perfect squared trinomial. Oh my Lanta. What happens here? One of those cancels out with that, and I get k plus 1 over k plus 2. Yay! Oh my gosh, let's do another one. All right, last one. Got some squareds going on here. So put a 1 in here. 2 times 1 all squared. Is that equal to 2/3 times 1 times 1 plus 1 times 2 times 1 plus 1? Tis. Whoops, I'm sorry. Copy and paste. Prove. So copy and paste again. And replace with the next term. So the next term would be 2 times k plus 1 squared. What happens when you put a k plus 1 in there? And what happens when you put a k plus 1 there? You get 2k plus 2 plus 1. Right? All right, now, I wanted to do this one with you because I wanted to show you a little trick that I learned as I did lots and lots of these and made mistakes and had to go clean up and had to figure things out and no Google to try to find out where I was, what I did wrong or whatever, but just the struggle was real. So remember, I do know that I'm going to replace that, right? That part is going to be replaced with something that's not super better, right? Right, I replaced it with its rule. But then, oops, I forgot, I kind of went on the wrong side of that plus sign. This is adding, and I didn't clean this up. And here's what I noticed. I've got 3 factors over here with they're all over the denominator of 3. And one of the factors is a k plus 1. So notice where I'm trying to go. One of the factors is a k plus 1, and everybody is on top of a 3. And I notice in my first term here, I've got a k plus 1 and a division by 3. I also have a k plus 1 here, right? I don't want to distribute that 2 through yet. Now, trust me, when I first did these problems a long time ago, I did. That's exactly what I did. And then things just went awry, and so I had to go back and try again. Try again. So what I'm going to do is use my exponent rules here. Whoops, I don't want white. And what I'm going to do here is say, right, remember what you did, what is a times b squared? Isn't that a squared b squared? So I'm going to write a big long fraction with a 3 under it. And I'm going to write 2k times k plus 1 and then this is 4. But watch how I'm going to write my 4. This is 2 squared times k plus 1 squared. Now, why would I do such a thing? Look at here's a plus. I can pull a k plus 1 out of the left side, 1k plus 1 out of the left, to the left of the plus sign, to the right on the plus sign. What can I also pull out? And it's all on top of 3, right? Kind of crazy. So see what I'm doing here? So I'm going to pull that 2, that k plus 1, all over 3, out. And what do I have left? What do I have in here? Make sure I did that right. Oh, I messed something up. Do you see what I did? You see what I did? Sorry about that. I could already tell by the way that was factoring that I made a mistake. See, I was so clever. I wanted to highlight that 2 times 2. Let me do something before this step. So remember, this is all over 3, or this 2/3 here, right, is all with this part. This does not have a denominator of 3. So I just forgot to, I was making sure that I got this squared piece and showing you how to do that. But don't forget that I also want this to be on top of 3, but that's not legal until I multiply everybody by 3 here. Now I can put everybody on top of the one fraction, or again, I can just say, highlight and say these are the things that I'm going to take out front, right? So I'm going to take out the 2/3, everything in white. I'm going to take out the k plus 1, right? 2/3 is common to both. K plus 1 is common to both. And then what's left is that k, that 2k plus 1, the plus, and the 6 times k plus 1. Right? You're going to make mistakes like this too, so just be patient and go back. And it was when I knew this was supposed to work out, and that factoring that I got down to wasn't going to give me the factors I wanted. So I knew there was something I had missed. So now when I work in here, this is 2k squared plus k plus 6k plus 6, which is 2k squared plus 7k plus 6, with this 2/3 k plus 1. And then sure enough, now things are better, right? I have 2k plus 3 and k plus 2. That's what I wanted. I already knew I had these. I wanted to get these, verify it works. 2k times k is 2k squared. 4k plus 3k is my 7k. 3 times 2 is my 6. Woo! Phew! All right. So your homework is a handout, right? And practice, there's 5 of them to practice. Struggle, talk to one another, try to get through it. I've tried to make sure that all the examples that I did showed you enough to be able to handle the 5 problems that I chose for homework. So I hope it goes well. Take care, and I will see you in quotes soon.